So just like both the enthalpy and entropy terms that we've talked about, both in this class and before, we can think about tabulating the energy change between the reactants and the products, and we often do that initially in the standard state. And the reason for that is because if you don't have sort of everything at a comparable state, then the actual energy change is sort of useless as a comparator. You can't compare a bunch of different reactions in a book if they're all being operated at very different conditions. So the standard state is simply just like a proxy for like room temperature conditions that allows all reactions to be computed under those conditions so that they can be directly compared under identical conditions. And so just the same as enthalpy and entropy, we have standard free energy change for delta G, and we use the little degree symbol there. And so delta G naught captures both delta H naught and delta S naught. So it's important to remember that the expression that we talked about before still stands T delta S. This is true, but if we're talking about computing the free energy change under standard conditions, then built into that means that the enthalpy and the entropy change are also under standard conditions. So what are standard conditions? Well, if we have pure substances, then we expect them to be in pure form and existing at 1 atmosphere of pressure. If we have solutions of something that's dissolved, we expect their concentrations to be at 1 molar, and we expect the temperature of the system to be at 25 C, which is slightly above normal room temperature, but we're often working in Kelvin, so 298.15 Kelvin. So that's what that means. It's just a sort of it's just a value that allows us to make direct comparisons as to other reactions, assuming everything's under identical. So another sort of nuanced form of that free energy change under standard conditions is the free energy change of formation. And back in 107 we had a very similar term, which was delta H of formation. And really that's the energy change for one substance. So it's the energy that it takes to produce that substance, 1 mole of that under standard temperature and pressure conditions. And this is different than the delta G naught generically, because that's for a reaction. So that's the change for a reaction generically. So A plus B goes to C plus D. We could compute the free energy change of the products minus the reactants, and that would give us the overall free energy change under standard temperature pressure conditions. Delta G formation is a specific type of reaction where it's accounting for essentially the birth of a particular molecule. So an example of that could be like carbon from its pure elements plus sort of 2 hydrogen gases. Both these are their pure elemental forms to produce methane gas. This would have a delta G of formation because this is how much energy it took to form 1 mole of that particular substance. These two things can be the same, so we could have a delta G of reaction for this and it would be the same as delta G of formation, but we can't have a delta G of formation for a system where we're interconverting multiple reactants and products. So this is a distinct idea. Another example of that might be, say, the formation of ammonia from its pure elemental forms of nitrogen and hydrogen. In this case, the delta G of the reaction is minus 33 kilojoules. And what that's telling us is that these things under standard temperature and pressure conditions for the reaction as it's written right here, that has a decrease in overall free energy of 33 kilojoules for the reaction as written. But this is not quite the same as delta G formation because, remember, delta G formation is for 1 mole of the substance. This is written out as written for 2 moles of the substance. So this would be actually minus 33 kilojoules divided by 2 moles, and that would give us half of that, 16.5 kilojoules per single mole. You know, we could have written this reaction up slightly different, and that would have given us the same thing. We could have said, well, actually it's, you know, a half nitrogen plus 3 halves hydrogen makes 1 mole of NH3, and then the delta G reaction for this system would have been minus 16.5 kilojoules. And then the delta G formation and the delta G reaction would have been the same. So it's important to know that when we're talking about formation energies, we're talking about individual moles. So the formation energy, sort of by convention, of a pure element in its most stable form, we would say, something like carbon as an element. Its most stable form is graphite. Carbon can actually exist in lots of different phases. We call those allotropes. So carbon could be graphite. It can be what's called glassy or vitreous. It could be in a nanotube. It could be in all sorts of different forms. But graphite is the most stable form, the lowest energy form. And sort of by convention, we just say that that's zero. And that sort of fits with our other definitions, where delta G is equal to delta H minus T delta S. And if you think back to Chem 107, we said something similar for pure substances for delta H. And for the third law of thermodynamics, we would say that that's zero as well for the purest form of that crystal, which would mean that makes sense that sort of this is zero. And all that's saying is that, well, let's take the most stable form of something and let's call it zero because that's the lowest energy. And then any difference in energy is relative to that most stable form. So if it takes more energy to arrange the atoms in glassy carbon compared to graphite carbon, then we know that. And so everything is referenced to its purest form of itself. And that's not a real number. That's not like a universal number. It doesn't actually take zero. It's just a referential number, because all we really concern ourselves with in energy typically is accounting for changes. In reactions, we want to know, is it more energy to have products than the reactant form, or is it less? We're not really concerned about the absolute energy of an individual compound or molecule. And so in that case, just saying that the change in energy to produce it is zero, it doesn't really affect our understanding at all. It's just sort of an accounting term.